The periodic table is set up based on the theory of repeating patterns, which is the periodic law. The periodic table as we use it is set up according to increasing atomic number. It's aligned so that valence electrons group families of elements. The most prominent families of elements are the alkali metals, group 1, alkaline earth metals, group 2, which are both metals. The transition metals are in the center of the periodic table. The lanthanide and actinide series, the F block, are part of the transition metals. The nonmetals on the right-hand side of the periodic table have two prominent groups. Group 18 are the noble gases. These are all gases with a complete set, an octet, of valence electrons. They are unreactive. Group 17 are the halogens. They are highly reactive because they have one vacancy to their octet. They have 7 valence electrons. Separating the metals from the nonmetals on the periodic table are the elements we refer to as the metalloids. The metalloids share properties with nonmetals and metals. The main group elements, the representative elements, are those from the S and P blocks. In these elements, we can see very clear patterns. We can see groupings of properties. We can see commonalities with electron structure and the reactivity of these elements. First, the valence electrons. In group 1, each of these elements has 1 valent electron. In group 2, these each have 2 valent electrons. Group 13, which is 3A, has 3 valent electrons. The next group, 14, also known as 4A, has 4 valent electrons. And this progresses 5, 6, 7, up to the noble gases, which have a complete octet of 8 valent electrons. We can analyze those valent electrons by looking at the electron configuration. Group 1 ends in S1. Group 2 ends in S2. Group 13, its last electron is the P1 electron, then P2, P3, P4, P5, and then finally the noble gases have the complete S2P6 electron configuration. Ions are charged atoms. If the atom becomes positively charged, it's referred to as a cation. And if it becomes negatively charged, it's called an anion. Because of the valent electrons, you can predict which groups or families of elements will form which type of ions. Because of electron affinity and the amount of energy required to remove electrons, groups 15, 16, and 17 are less likely to lose electrons, but are more likely to gain electrons. Gaining those negative particles gives those ions a negative charge. The charge they gain depends on how many electrons. The elements in group 15 become -3 ions. The elements in group 16 become -2 ions. And the elements in group 17 become -1 ions, because they'll only take on one more electron to the 7 valent electrons they already have to have that perfect noble gas state. On the other side, groups 1, 2, and 13 become ions with a positive charge. Those in group 1 become +1 ions, those in group 2 +2 ions, and those in group 13 +3 ion. This is because they only have 1, 2, and 3 valent electrons, and it takes much less energy to lose just a couple of electrons. Losing those negative particles results in a positive ion. Some examples of some popular ions include sodium and potassium. Each of these are alkali metals from group 1, and they become ions with a charge of +1. While elements such as magnesium and beryllium from group 2 lose their 2 valent electrons to become +2 ions. Aluminum is a popular cation. Because it's in group 13 and has 3 valent electrons, it becomes aluminum +3 as an ion. On the other side of the periodic table, an anion, such as phosphorus -3, would come from group 15 on the periodic table. Oxygen, -2, and sulfur, -2, are popular anions from group 16. All of the halogens are popular ions. They each form -1 ions because they're in group 17, meaning they have 7 valent electrons. They only require 1 more electron to reach that noble gas state, so they are more than happy to become -1 ions.